This video is part of an online course of multivariable calculus, and I'm going to talk about Stokes Theorem. Stokes Theorem says that the line integral of a vector field f over a closed curve C is equal to the double integral of curl of f dot ds over the surface S. Okay, so what is C, what is S, and what is F? So I'm going to start with F. F is a differentiable vector field, which means what? Which means that all components of F have continuous partial derivatives. Okay, and so F is a differentiable vector field. What is S? What is C? S is an oriented surface, okay, and it is bounded by the simple closed curve C with positive orientation. So these are basically the requirements for Stokes theorem. The vector field F is differentiable, S is an oriented surface with the boundary curve closed curve C, and with the positive orientation, then the integral of f dot dr is the double integral of curl over the surface S. If you remember, the notation that we used for curl was del operation cross product with f, and if I want to talk a little bit about the physical meaning, I can say that if f is the velocity of a fluid, then this integral is basically circulation of f around C, circulation of f around C, and it's equal to the summation, or basically the integral of rotation of f of the vector field F, and then if you remember, ds was n dot ds, where n is basically the normal vector, so the double integral of the perpendicular part of the rotation of f over s. Okay, so now let's talk about the positive orientation. What do I mean by the positive orientation here? So let S be an oriented surface with the boundary curve C. Boundary curve C. So we have something like that. We have a boundary curve C, and we have a surface S. Okay, orientation of C, of actually S, induces a positive orientation on S, on C. Okay, so how do we do that? Well, we say that if you walk, I'm gonna write everything down. If you walk in the positive direction of C, in the positive direction of C, such that your head is pointing in the direction of N, where N was the normal vector of the surface N, of the surface S, okay? Then S will always be on your left. Okay, so I say that I have a surface S that is orientable, which means that I have an orientation N here, and then this orientation induces an orientation on C. How? If I walk in the positive direction of C, then my head is pointing the direction of N, the surface S should be on my left. Otherwise, if you step to the right, you will fall off the edges of the surface. Okay, and in that case, if we have all these three situations, we say that orientation of S and C are compatible, and this compatible orientation is the one that we use in Stokes Theorem in here. So the orientation of S and C should be compatible, which means that if you walk along the positive direction of C such that your head is in the direction of M, then the surface S would be on your left. Let's look at some example to see how we can find that. Let's have the surface S as, for example, top half of a sphere, and this is our S. The curve C, which would be the boundary curve, is this one, and the direction of the curve C is given. What do you think about the direction of S? Which means that where is N? Okay, so if I walk along C, okay, and I want the surface S to be on my left, then my head, which would be in that direction, shows N. So the direction of S would be given when the direction of C is given. Let's look at another example. I'm going to consider a cylinder which is bounded on top and bottom by, for example, the plane Z equals to 0 and Z equals to 5, for example. Then this cylinder has two boundary curves. One is the circle on the bottom and the other one would be the circle on the top. Okay, I'm gonna call this one C1, I'm gonna call this one C2. The direction of S, this is our S, the direction of S is given as the outward orientation, like this, and then I need to find the direction of C1 and C2. Okay, let's look at C1 first. So I need to walk like this along the curve C1 such that my head is pointing N, and then I want the curve C, the surface S, to be on my left. Therefore, the positive orientation of C1 would be like that. Okay, now if I want to walk on C2 such that the surface S is on my left and my head is pointing in the direction of N, then C2 should be in that direction. So the positive direction of C1 and C2, as you see, they're opposite of each other, and both of them are compatible with the surface S. Okay, so that's the compatible orientation, or something that we call positive orientation in Stokes theorem. Let's look at one example. Example is this: let f be p, q, and 0, where p and q are functions of x and y, and let s be a domain in xy plane with upward orientation. Let me graph s first. So x-axis, y-axis, and then z-axis. Okay, so I have a surface S in xy plane with the boundary curve C. The orientation of S is given as upward orientation. Okay, and so if I want to write orientation of C, it should be counterclockwise like that, such that if I walk along C in the positive direction, such that S would be on my left and my head would be on the direction of N, then C would be counterclockwise. Okay, so I'm gonna confirm Stokes theorem here. Stokes theorem says what? It says that the integral of f dot dr over the curve C is the double integral of curl of f ds over the surface S. Okay, I'm gonna start with the right hand side, and I'm gonna calculate curl of f. If you remember the formula of curl, it was determinant of this matrix I, j, k, partial derivative with respect to x, with respect to y, and then with respect to z, and then I'm gonna put f on the last row, p, q, and 0. Okay, so the first coordinate would be, I'm gonna remove the first row, the first column. I'm gonna find determinant of this minor, which would be q with respect to z, and then the second one would be p with respect to z, and then the last one would be q with respect to x minus p with respect to y, qx minus py. Let me move this one a little bit. Okay, minus p with respect to y. That was the curl. And then I know that ds in the surface integral is equal to n ds, where n is the normal vector of our surface. So it's the unit normal vector. I can take this at 0, 0, 1. So I'm gonna put 0, 0, 1, and then the element of surface area. And so the double integral of curl of f ds over the surface S would be equal to what? Q with respect to z, p with respect to z, and then qx minus py, dot product with n, and then ds. Okay, so calculating this dot product in here, I just get q with respect to x minus p with respect to y over the surface S, and then as you see, I have ds in here. So ds is the element of the surface area, but our surface is in xy plane. That's why ds in here would be equal to basically dA that we use in double integrals. Okay, so now let's look at our Stokes theorem. We say that by Stokes theorem, the line integral over the closed curve C of our vector field is equal to the double integral of qx minus py dA over the surface S. As you see, this surface S is a region in xy plane. So let me write that. So this is a region in xy plane. And so it looks familiar, right? It's Green's theorem. Green's theorem. So basically, Green's theorem is a special case of a Stokes theorem in which the surface is a flat surface in xy plane. Okay, so we just confirmed that Green's theorem is basically the two-dimensional case of Stokes theorem.